Good morning. In today's lecture, we discuss about a uniform boundedness theorem. The uniform boundedness theorem will tell us about the point-wise boundedness implies a uniform boundedness. And in the proof of this, we need the Berry's category theorem. So now we discuss the uniform boundedness theorem. So uniform boundedness theorem given by the Banach and Stanners in 1927. So it is also called the Banach-Stanners theorem. So this theorem gives sufficient condition for a sequence norm Tn to be bounded where X is a Banach space and Y is a norm space, and Tn is a bounded linear operator. It has a lot of applications like summability theory, analysis of Fourier series, V convergence, and to prove uniform boundedness theorem, we need the Berry category theorem. So first of all, we discuss about the category. Is let M is a subset of a metric space Xt, and then set M is said to be a real or nowhere dense in Xt if its closure M bar has no interior point. Or the set M is said to be of first category or measure in X if M is the union of countably many sets, each of which is real in Xt. For example, the set of rational numbers in R or in itself are of first category. Because let M is a set of all rational numbers, and we know that the Q is countable, the set of rational numbers is countable, so M is countable. And each xi belongs to be this set of irrational numbers. M is equal to the union of all these xi's. And each xi is real in Q or this M. M is said to be of a second category or non-measure in X if M is not measure or first category. For example, we have LP or L1 are the non-measure. Now we'll discuss the Berry category theorem. If a metric space is complete, if a non-empty metric space is complete, then it is a non-measure in itself. Hence, if a non-empty set is a complete and X is a union of all AIs, where AIs is closed, then at least one AI contains a non-empty open subset. Now we get the proof of this result. Suppose that the metric space X is non-empty and it is complete and of first category in itself. Then by definition, we have X is equal to be union of all MIs, where each MI is real in X. Now we have to construct a Cauchy sequence Pk whose limit, say P. Now because we have already given that the X is complete, so it will be existing up in there. So whose limit is P is not in this Mk, and this contradicts that X is equal to be union of all the MIs. Now, since by assumption M1 is a real in X, so by definition the closure of M1 does not contain a non-empty open set. But XD is complete, so every Cauchy sequence is convergent. So it will contain a non-empty set, say M1 closure is not equal to Bx, so M1 closure complement is equal to be X minus the M1 closure, which is a non-empty and the open. So we may choose a point P1 in this M1 closure complement and the open ball about this point B1 centered at the point P1 having a radius epsilon 1 subset of a closure of M1 complement, where epsilon 1 we consider is less than 1 by 2. Further, by assumption again the M2 is a real in X, so the closure of a M2 does not contain a non-empty open set, hence it does not contain an open ball, this BP1 epsilon 1 by 2. This implies that this ball about the point P1 intersection M2 complement closure is not empty and open, so we may choose an open ball in this set, say B2, which is equal to be the ball about the point P2 having radius epsilon 2, where epsilon 2 is less than epsilon of 1 over the 2. And by induction, we thus obtain a sequence of the balls Bk, where the epsilon k is less than 1 over 2 raised to power k, such that the Bk intersection Mk is empty. And hence, this Bk plus 1 is a subset of the B ball of having a center about the Pk subset of Bk. And since epsilon is less than 2 raised to power minus k, the sequence Pk of the center is Cauchy and converges because here the X is complete. So the Pk converges to Bp. Also for every m and n is greater than m, we have these balls, say Bn, subset of the balls around the point Pm, so that the distance between the Pm and the P is less than or equal to B, but the triangle inequality d of a Pm comma Pn plus d of a Pn comma P. Now since the Pn converges to be P, so we have, and the d of Pm is less than epsilon m over 2, so we get this converges to be epsilon m over 2 as n converges to be infinity. Hence P belongs to be Bm for every m. Since the ball here, the Bm is subset of a mm complement closure, so we now see that P does not belongs to be the m for every m. So that the P does not belongs to be union of all these m's, which is equal to Bx by the theorem. So this contradicts that the P belongs to be X, so hence the Barry's theorem is being proved. The converse of the Barry's theorem is not true. In fact, there are incomplete metric space which is non-measure and shown by the Barbachy incomplete norm space which is of second category. So from here the Barry's theorem we shall now easily obtain the desired uniform boundedness theorem. And this theorem states that if X is a Banach space and a sequence of operators Tn is bounded at every point, X belongs to be X and the sequence is uniformly bounded. In other words, you can say that the pointwise boundedness implies boundedness in some stronger sense, that is uniform boundedness. So now we discuss the theorem. So let sequence Tn be a sequence of a bounded linear operators where Tn is from x to y, where x is a Banach space and y is a norm space, such that the sequence norm Tnx is bounded for every x belongs to be x, that is, say, norm of a Tnx is less than or equal to be Cx, where Cx is a real number depend upon some x. Then the sequence of a norm Tn is bounded, that is, there is a C independent of Ax, such the norm of a Tn is less than or equal to be C. So here we can say that the pointwise boundedness of the operators Tn is uniformly bounded. So now we discuss the proof. So for every k belongs to be naturals, let ak, the subset of ax, be the set of all x such that the norm of a Tnx is less than or equal to be k for all n. And it is being given that suppose that the ak is closed. Indeed, for any x belongs to be a closure of a ak, there is a sequence xj in ak converging to be x. This means that for every fixed n we have norm of a Tnxj is less than or equal to be k, and we obtain norm of a Tnx is less than or equal to be k. Because here it is given that the TNS is continuous and so is the norm. Hence X belongs to be AK and AK is closed, so we have proved that the AK is closed. So now the norm of a TNX sequence is bounded. So each X belongs to be X belongs to be some AK, hence we have a X is equal to be the union of all those AKs. Since X is complete, so by the Barry's category theorem, there is some AK contains an open ball. Say the B naught is equal to be the Bx naught around the point x naught having a radius r, a subset of this AK. So let x be any arbitrary non-zero element in this set x, and we set z as a x naught plus gamma x, where the gamma is equal to be r over 2 times the norm of x. Then the norm of z minus x naught is less than or equal to b r. So the z belongs to be b naught. Hence, from the definition of AK and the B naught, we obtain that the norm of a T and Z is less than or equal to be K naught for all n. Also, the norm of a T and X naught is less than or equal to be K naught since the X naught belongs to be B naught. Therefore, we obtain the X is equal to be Z minus the X naught over gamma. And for all n, we get norm of a T and X is equal to be the norm of a T and z minus the x naught over the gamma, which is less than equal to be 1 by gamma norm of a t and z plus norm of a t and x naught. So which is less than equal to be, because here the norm of a t and z, we have already gone through the previous cases out here. So this is less than equal to be 4 over r norm of a x into the k naught. Hence for all n, norm of a tn, which is equal to the supremum of a norm of a tn x over the x, norm of a x is equal to be 1. This is less than equal to be 4 by r k naught. By considering the c as a 4 by r k naught, we can say the norm of a tn is less than equal to be c. Hence we get the result. Now considering the application part of this theorem, we consider the space of a polynomials. So in the norm space X of all the polynomials with the norm defined by the norm of Ax is equal to be maximum of alpha I over the I, where alpha naught, alpha 1 are the coefficients of Ax, is not complete. So we construct a sequence of bounded linear operators on Ax which satisfies the norm of a T n x which is less than Cx but not norm of a T n x less than equal to be C. So that we can prove that the X is not complete. So we may write polynomials x is not equal to 0 of degree nx in the form that xt is equal to be summation of alpha j tj, where alpha is j is equal to be 0 for all j greater than nx. As a sequence of the operators on x, we take a sequence of functions, say tn is equal to be fn defined by tn as 0 is equal to be fn0 is equal to be 0 and tnx is equal to be fnx is equal to be alpha naught alpha 1 plus alpha 1 plus so on alpha n minus 1. Here this Fn is a linear and bounded here because here the modulus of alpha j is less than equal to be norm of Ax. So that the modulus of Fnx is less than equal to be n times the norm of Ax. Furthermore, for each fixed x belongs to be x, the sequence Fnx satisfies the norm of a Tnx less than equal to be Cx because a polynomial x of a degree nx has nx plus 1 coefficients. So we have the modulus of Fnx is less than equal to b nx plus 1 maximum of alpha j, which is equal to be Ca. So now we have to show that the sequence Fnx does not satisfy the norm of Tnx less than equal to c. That is, there is no c such that the sequence Fnx satisfies norm of a Tn is equal to be norm of a Fn less than equal to be c for all n. So for Fn, we choose a x defined by xt is equal to be 1 plus t plus so on t raised to power n. Then norm of a x is equal to be maximum of alpha I over the I, which is equal to be 1. And Fnx is equal to be 1 plus so on 1, which is equal to be n, which is equal to be n times the norm of Ax. Hence, the norm of Fn is greater than equal to be modulus of Fnx over the norm of Ax, which is equal to be n. Here the n is any arbitrary, so the sequence Fn is unbounded. Hence we get the result. So thank you.